So this is the positive direction, this is the negative direction. This is your y-axis, positive going this way, negative going here, so mad that way. And we have a z direction, which is vertical, positive being up to the ceiling, negative being to the floor. Yes? Now, once we set up this coordinate system, we are in three-dimensional Euclidean space, R3. So that means every tip of everyone's nose has a coordinate, a unique coordinate, as long as we agree on units. So let's say our unit is this much. This is 1 unit on every axis. Okay. So what is the coordinate of my nose? First hand. Yes.
5 units of.
So the coordinate, we have R3. Each point has 3 coordinates.
0, 0, 5.
0, 0, 5. Maths is onto it. Okay, 0 for x, 0 for y, 5 units approximately for z. Okay? Think about coordinates of your noses. Can you figure them out? Yes, with some time, right, in approximation, you are unique in this system, coordinate system. Cool? Now we're placing a graph of a function of 2 variables in this coordinate system. This is our domain. This is xy plane. Each point from this domain is assigned a point on my umbrella surface. This is your function. This is the rule that describes that transformation from xy plane onto something else. And here comes my helper. Here, and here, and like this. So my claim is that this cloth of the blue, just the blue cloth, not the stick, is a graph of a function of 2 variables. So the domain is somewhere here, and this is the rule that sends each point from here to some point on my umbrella. I'm not asking you to write the equation. It will not be on the exam. The equation is a little bit complicated because of these middle parts and stuff. Just turn the shape this way. Cool. Now the coordinate of this point, the center point of my umbrella, is 10 or 0, 0, 10. So my nose was 5, was 0, 0, 5. This is 0, 0, 10. Approximately. We're not sending rockets into space here. Just here. Okay. So partial derivatives. How do we differentiate this surface? What does it mean? So I'm going to show you geometrical interpretation of the notion of partial derivative. Firstly, the notion of a partial derivative is a local notion. What do I mean by local? It is attached to a point. So when you look at the definition of a partial derivative, the definition starts with, for this point x naught, y naught, blah, blah, blah. So a point from the domain is chosen, and for this point, this notion is defined. Okay, so let's choose a point. Choosing a point, right here. Yeah, and I'm going to name it. I will call it x naught, comma, y naught. So if you see me on the streets when it's raining, have a look. The point will still be there. And you will not feel like there's something wrong with me, right? It will all make perfect sense to you guys. That's good. So this is the point. X naught, y naught live in a domain. So it's a point here. X naught, y naught. Here. And it's elevated by this function to this z height above the disk. So this function is in altitude above the disk. The rule that tells you where to send these points, how high they go. Cool. What does it mean to differentiate partially at this point with respect to x? How do we differentiate with respect to x? So f sub x, just like we did, we tried to find some problems that you usually ask to find partial derivative of this function. What does it mean? So that means we are ignoring the change in the y direction. So the y coordinates don't change, they're fixed. We treat them as constants. Geometrically, what does it mean? That means that I am selecting points on my umbrella that have the same y coordinate. And that looks like a curve that passes through this point and looks like this. This is a cross section of my umbrella. Look, what is the same about all these points on the green chord? They're all on the umbrella and they all have the same y coordinate. What's the y coordinate? First hand. Yeah. You want to say it? I mean, it's approximation, right? Yes? Right? Yeah, yes. If we say unit is like this, can you guesstimate it? Plus or minus? Got it. He's earned his chocolate. Well done. The truffle. Come here. Ready? Gotcha. Oh! Bravo. Okay, so what are we doing? The points on this green chord all have the same y coordinate, -2. So we can ignore it. It doesn't change, doesn't add any additional information to us. But that means we are back to stage 1 mathematics. We're back to functions of one variable. This chord is a function of a graphable function of one variable. And we've got all the techniques that we've learned in stage 1 mathematics, how to differentiate things, right, of that nature. So the notion of rate of change of this function at this point is now coincides with the notion of the rate of change of the green function with respect to change in the x direction. Geometric interpretation is the slope of the tangent line. So at this point, all we need to look at is what is the slope of the tangent line to the green curve. What is it? What's the number? Slope of the tangent line. Yes, 0. So the rate of change in z variable with respect to x variable. X changes, what happens to the height? Well, at this point, x naught, y naught, nothing's happening. The tangent line is horizontal. That means the value of the partial derivative is 0. And that is a special number, and you'll remember it, and we'll refer to it later. Now, partial derivative with respect to y. What do we do? For the same point, what do we do? We are fixing x coordinates. We're finding that curve that passes through this point that has the same x coordinate, x naught, or we can guess it, it's 0, right? The way I position this umbrella, x naught is 0. So that's your chord, y chord. Better understanding, I'm sure. So we are cross-secting my umbrella with this white curve, and all the points in the white curve have the same x coordinates. So the question of finding the partial derivative of z with respect to y, or f sub y, is now reduced to the question, what is the slope of the tangent line at this point with respect to the y curve? White curve. White, not y. So what's the slope? I know you can't see well, but yes.
-1/3.
Okay, so negative or positive. Change in y, for one change in y in the positive direction, what change do we have in the z direction? Right, this is a slope. One change in this direction, y, which is this x, positive being this way. And what change do we have in the z direction? So vertical direction?
1.
1, I'll take 1. Because you guys can't see it. But if we rotate the umbrella, let's just cheat a little bit, changing coordinate system so you can see better. This is your slope, this is a slope. So for one change in this direction, you have one change in the vertical direction. So it's slope 1. So at this point, we have two special numbers. 0 is the rate of change with respect to x, and 1 is the rate of change with respect to y. Those are your values of partial derivatives. And they inform you, they will tell us a lot of information about the particular behavior of this function in the neighborhood of this point. We'll look at it later. But in the last topic of 108, to finish up the revision, was if you've got two lines, yeah, one is the tangent line for this direction, the other one is the tangent line for that direction. Two lines in free space. Yeah, if you put a plane on top of them, plane passes through those two lines and touches the surface at that point. What's the name of the plane? How do we call it? The tangent planes. Thank you.